One thing we might think about when we're thinking about real gases is how does a gas know what the temperature is, or the pressure, or even the volume for that matter? The scales that we use, the metric system and all of that, are purely our invention. And in fact, real particles, have no reference point with which to judge those things. So we might have to think in terms of how does a molecule detect these things. So for example, we know already that the temperature is related to the average velocity of the particles. So that is one way that molecules might be able to at least have a sense of what the temperature might be. We also know that the volume, or the molar volume, somehow is based on a relative scale, and it's relative to molecular size. Finally, for pressure, this is something that is a balance between the velocity on the one hand, which of course is related to the pressure or the force that they would exert on the container walls, and the intermolecular forces. So these are the sorts of indicators that a molecule might use to judge what is a temperature, what is a volume, and what is a pressure. But the Kelvin scale has no meaning for a molecule other than absolute zero. The metric system of measurement of volume has no meaning for a molecule. Why would it care about the volume of a cubic centimeter, for example? So instead, one thing we need to look for is what are the reference points that a molecule might care about? What are the things that it has that we should be wary of and allow it to use in terms of defining its state? Well, I'll note that every molecule, every substance, has a critical point. What if we use that as our reference point for how we measure temperature, volume, and pressure? So, for example, we might create what I'll call reduced properties that would be defined as follows. I would define the reduced temperature as the actual temperature, and let me make a little subscript R for reduced, as the actual temperature over the critical temperature. So now we're going to scale all the temperatures by the critical temperature. And so the critical temperature represents a temperature of 1, or reduced temperature of 1. The molar volume in the reduced scale would be the actual molar volume divided by the critical molar volume. So again, we're using the critical value as sort of a size scale that will help us moderate this. And the reduced pressure would simply be the actual pressure divided by the critical pressure. So if we define these critical variables in this way, so that they are reduced now, how does that affect some of the things that we look at in terms of their value, like compressibility factor? Well, let's take our compressibility factor, and we've been writing it as essentially the P times molar volume over RT. Well, what if we change this now to looking at the reduced pressure times the reduced volume over R over the reduced temperature? And actually, you don't necessarily define it exactly this way, although I suppose you could. But when we do this, it turns out that we see the following behavior. And so it's drawn over here on this diagram. And what are we looking at here? We are looking at the compressibility factor for a number of different substances. So all of the substances that are included are in this key over here on the lower right. Now, in each case, what we have done is we have expressed the pressure, volume, and temperature in reduced coordinates. So in other words, we've scaled those for each of these particular molecules by their critical values. And then when we plot them on this plot of the compressibility factor versus the reduced pressure, so this is the reduced compressibility factor, the reduced pressure, we find that in fact all of these molecules tend to lie on the same line. So look at this. These are a whole bunch of different molecules, and they all lie on this line. There is nothing about their individual characteristics, their individual intermolecular forces or anything that cause them to stray very far from this line. And that's true at all of these reduced temperatures. This is the same compressibility factor plotted for various values of the reduced temperature. So this really amazing relationship, I think, between different molecules is something that we call the law of corresponding states. And it basically says that these molecules all tend to follow very similar behavior. In other words, there is a universal behavior in molecules that we can now detect when we plot them in their reduced coordinates, that is, relative to their critical values. Now, it turns out some of these models that we've talked about actually capture this law of corresponding states, this universal behavior. So let me remind you that for the van der Waals model, we found that the critical volume, molar volume, was equal to 3 times this parameter B. We found that the critical pressure was equal to A over 27 times B squared. And then we found that we could relate the critical temperature to 8A over 27B times R. All right, so using these 3 values for the van der Waals model, let's define the reduced properties as we have up here and rewrite the van der Waals equation of state. So what would that van der Waals equation of state look like in these reduced coordinates? Well, I'm going to let you actually work this out on your own, but I'll give you the final answer so you can test to see if you actually get the same thing. But what I get is I find that 1 over 27 times the reduced pressure plus 1 over 9 times the reduced molar volume squared times 3 times the reduced molar volume minus 1 is equal to the reduced temperature times 8 over 27. Now take a look at this equation. I've got reduced pressure, reduced volume, reduced molar volume, and reduced temperature. But there is nowhere in this equation that you can see the parameters A and B. So in other words, this equation of state would hold for any molecule when it's expressed as a van der Waals gas, but using its reduced properties. All right, so this in part is what feeds the reality of this law of corresponding states. And in fact, I could go a step further and use these new scaled parameters to write down the compressibility factor for the van der Waals gas, and I would get an equation that looks like this. The reduced molar volume divided by the reduced molar volume minus 1/3 minus 9 over 8 times the reduced molar volume times the reduced molar temperature. Sorry, the reduced temperature. So again, our compressibility factor is completely independent of all of the parameters that would make each molecule unique or each molecule separate from each other by their molecular characteristics. So this law of corresponding states, it turns out, is going to be very handy because when we really do need to account for the non-ideality of gases, basically it says that if we express things in terms of reduced parameters, in terms of reduced properties, we can always get a universal behavior for how that reduced compressibility factor changes with those reduced parameters. In other words, we don't have to recalculate for each individual molecule exactly what their non-ideality is. We can use this law of corresponding states now to basically tabulate values for ourselves that will allow us to correlate what amounts to the non-ideal behavior of any substance, as long as it sort of fits this law of corresponding states.